Welcome to the Biomedical Data Science series. In today's lecture, we're going to talk about statistical learning, specifically regression. However, we're going to talk about regression as an aspect of machine learning. So the first question is, what is machine learning? According to Professor Tom Mitchell's definition, a computer program is said to learn from experience E with respect to some task T and some performance measure P if its performance on T as measured by P improves with experience E. Now, what does this statement actually mean? Learning from experience is something that's very natural to human beings. Think about a child who is trying to identify dogs versus cats. So when we try to teach a child that this is a dog versus this is a cat, we don't really discuss the entire anatomy of different breeds of dogs and teach it to the child, so that when the child next encounters a dog, that child can actually understand whether it's a dog or not. Rather, we show him a picture of a dog. And I tell the child that, hey, this is a picture of a dog. This is a picture of a cat, or when it encounters it in real life, it can identify that it's a dog or a cat. As the child encounters different breeds of dogs, different shapes and sizes of dogs, it can identify a dog and a cat without having to learn every details of the anatomy. This is called learning from experience, which is very natural to human beings. But the question is, can we ask a machine to do something similar? For example, suppose I want the machine to do a particular task, which is to differentiate an image of a dog versus an image of a cat. So instead of trying to code several thousands of lines trying to describe what are the different possibilities that an image of a dog might look like, which could be huge variability because of different breeds, different backgrounds, different sizes, and so on. Rather, I give them the image of a dog and I simply tell the machine that, hey, this is the image of a dog. Then I give some examples of an image of cats. And I let the machine identify the patterns by itself, so that as the machine gains more experience, that means as it's exposed to more and more images of dogs and more images of cats, the machine can identify the underlying patterns itself and be able to differentiate an image of a cat from the image of a dog. This is the machine learning version of learning from experience and being able to perform better. That means able to differentiate between the image of a dog versus the image of a cat better. Now, there are several aspects of machine learning. In this seminar series, we are going to focus on what is called supervised learning and what is unsupervised learning. Supervised learning are those cases where I actually tell the machine the right answers. So in the cat versus dog example, it would be an example of supervised learning, because after showing them the image of a dog, I actually tell the machine that, hey, this is the image of a dog. So the machine knows the right answer. So this is called supervised learning. In some cases, I do not provide the correct answer to the machine, and I let the machine come up with the pattern by itself. And that would be unsupervised learning. In this chapter, we are going to talk about regression as an example of supervised learning. So what happens in regression is that we study the relationship between different variables. Usually there is one variable based on which I would like to understand how a different variable behaves. So if there are two variables, we would like to see and identify patterns in how these two variables behave among themselves. So as a quick example to explain the concept of regression better, there is a cars dataset that's inbuilt within R. So if we look at the cars dataset and I use the str function to understand the structure of this dataset, it is a data frame which has 50 observations on two variables. So there are 50 cars which have a certain speed, And then the car is trying to come to a stop. And we are trying to check if there is a pattern between the car's speed and the distance needed to stop. One way to have a look at the pattern is to look at a scatter plot. So we plot the car's speed on the x-axis and we plot the car's distance on the y-axis. And if we look at the scatter plot, we immediately see a pattern that as the car's speed increases, the distance needed to stop the car increases. And if you think about it, it's quite natural that that would be the case, right? But what we want to do is we want to extract this overall pattern that the distance needed to stop increases as the car speed increases to a model, and that is a regression model. Usually, the car speed, which we are using to try to understand if we can explain the distance needed to stop, this variable car speed is called a predictor. The response variable is the other variable which we are trying to understand. And we are trying to explain how the distance needed to stop varies through its relationship with the other variable, car speed. So to summarize, there is a response variable, which is usually denoted by y, and there can be one or more predictors denoted by x. And so through the regression analysis, what we want to do is we want to study the effect of the predictors on the response. The first case is when there is only one predictor, and that case is called simple linear regression. So the idea of simple linear regression is we would like to extract this overall pattern and we would like to summarize it with a straight line. So what we are trying to extract here is there a linear pattern between the predictor x and the response y? And mathematically, we would like to write this linear relationship as y equal to an intercept term beta naught plus a slope term beta 1 times the predictor plus some random noise terms. Now, it is very important to understand the concept of these random noise terms. So if you go back to the data set, notice that the speed for two cars is the same, it's 4, but the distance required to stop is different. And that is because there are two different drivers, probably two different cars, two different models. And all these different aspects can bring different values to the response variable. But that is not what we're interested in. What we are interested in is there an overall pattern between the predictor and the response. We are not interested in the individual idiosyncrasies of each of the observations. So that becomes noise. That is not what we are interested in. So when we are trying to extract this pattern and we are extracting the linear pattern, that means we are trying to understand this linear, the intercept term and the slope term. So these two terms, the intercept and the slope terms, beta naught and beta 1, they become the model parameters. These are the terms that we are trying to estimate. These are the terms that the machine is trying to learn through experience. And by experience, I mean through these data points. The more data points the machine has, the better its guess of the intercept term and the slope term is going to be. So let us try to work with a publicly available data set that records the average weight of brain and body for a number of mammal species. So if you run this particular cell, you are going to get the data set. The data set can be loaded using the read.table function. The head function just displays the first few rows, which helps us understand what the data set looks like. So as you can see that the variable df that stores the data set is actually a data frame, and it has 3 columns. The first is the index, which is like the mammal number, and the second column has the brain weights, and the third column has the body weights. The data types are mentioned here, we know that the indices are integers and the brain weights and the body weights are numerical values. If you want to find out how many observations are there in this data frame, you can use the nrow function and check that there are 62 observations. So the problem here is we would like to identify if the brain weights of the mammals affect their body weights. Specifically, we want to figure out if there is a linear trend or a linear pattern in how the two variables behave. The function in R that is used to fit a linear regression is called LM. We are going to come to that later. But for now, let's try to look at the scatter plot of these two variables. So we use the plot function and we access the two variables using the $sign and we plot it. So as soon as we plot it and we have a overall linear fit here, and we are trying to understand what this plot looks like. First of all, notice that there are 3 points which are very large body weights greater than 1000, because of which the scatter plot is difficult to understand, difficult to see. In this scatter plot, if you simply use the plot function, you are going to get the scatter plot, but not the blue line. The align function adds a blue line, to an already existing plot. The line that we are adding here is the linear fit, which is done using the LM function. So what the LM function does is it does a linear fit of the response till the predictor. That's the overall form of this function. So we want to predict the body weight. So the response is the body weight given the predictor brain weight, where my data is stored in the variable df. And the color of this line is chosen to be blue, which is why we have a blue line. And so since we have these 3 large points that makes the other data points difficult to see, we are going to learn a little bit of data manipulation, and we are going to work with a shorter data set by removing these 3 points from the data set. So how do we access these 3 specific observations? Notice that these 3 observations correspond to body weight greater than 1000. I can access the row numbers corresponding to these 2 observations by using the which function. So if you do which df$ body weight greater than 1000, this is going to return to you the row numbers corresponding to which the body weights are greater than 1000. So I can look at those specific row numbers and then remove them, indicated by the negative sign, and then get all the columns. And then I store it in a different data frame, df1. We can use the LM function, as we saw before, to fit the linear model. And we are going to use the df1 dataset that does not contain these 3 large points to analyze the linear model. So notice that in the first line here, the variable lm1.fit, that name stores the linear model. So if you want to understand the details of this linear model, you use the summary function. We use summary of this variable lm1.fit to read the details of the linear model. And we get quite a lot of output over here. So let us try to understand each of these output in details. First of all, we have the call portion, where R simply displays the output and the formula. We have the linear model where the formula is body weight is the response and brain weight is the predictor. And we use df1 as the data. The next part of the output talks about the residuals. Remember that the concept of residuals comes from the fact that we are trying to predict the response given the predictors. So if we go back to the linear model, at the end of the day, we are going to have a guess of the intercept term, a guess of the correct slope term. And then by plugging in the value of different predictors, we have a predicted value of the response. And that is the idea of prediction modeling, like predictive modeling. So by residual, we mean that how much error we made on these observations when we replace the actual observations by the predicted observations. So we have the observed values of the response and the predicted values based on that equation that we just saw. And we have the residuals. The residuals would be negative if the observed value is less than the predicted value. And it would be positive if the observed value is greater than the predicted value. And then we can look at the distribution of the residuals. So for example, we can look at the median, the first quartile, the third quartile, the minimum and the maximum, which together forms the 5-point summary. The next section of the output, if we go here, talks about the coefficients that we are most interested in, right? So the first column of the coefficients gives you the current guesses. So based on this experience, that is the given observations, the current guesses that the machine makes is that the intercept term is 36.57 and the slope term corresponding to the predictor brain weight is 1.2284. The second column, standard error, measures the amount that the coefficient estimates vary from the actual average value of the response variable. The way that you can interpret it is the amount of error we are making while trying to estimate the coefficients. So we would like these errors to be small with respect to the estimate values. The third column is the t-value. The t-value is a measure of how many standard deviations the coefficient estimate is away from zero. When the t-value is away from zero, that means that there is some interaction. So corresponding to the intercept term, it means that in the presence of the predictor brain weight, the intercept term is 3.3 standard deviations away from zero. Corresponding to the brain weight, it means that the slope term is 14 standard deviations away from zero. Now, are these deviations from zero significant or not? That is given by the last column, which corresponds to the p-values. So let's talk about this in a bit more details. So this column gives you the probability of observing any value that is greater than or equal to the t-values that you observed in the previous column. This probability gives you the p-values corresponding to the hypothesis test, which checks if these estimates are significantly different from zero or not. So corresponding to the intercept term, a p-value of 0.00148 gives you the evidence that in the presence of the predictor brain weight, the intercept term is zero or not. Corresponding to the coefficient of brain weight, we get the p-value corresponding to whether the value 1.22 is significantly different from zero or not. Notice that we are particularly interested in the slope term because a slope term equal to zero corresponds to the fact that the predictor and the response are not really linearly related. So if this p-value is significantly small, that means that these observations, that this data set are giving us significant evidence that there exists a linear relationship between the predictor and the response. And these levels of significance are given by the significance codes. For example, 3 asterisk shows that there is a very high significance, a very high evidence that there is a linear relationship between the predictor and the response. Next, we look at the residual standard error. The residual standard error is a measure of the quality of this regression fit. That means, on an average, how much does the actual response observations deviate from the linear fit, from the regression line that we are using to summarize the overall pattern? So it's given as a formula, it's a square root of the residual sum of squares divided by residual degrees of freedom. What is residual sum of squares? Well, we talked about residues earlier, residuals. So that means we take the actual observations and we subtract the predicted values of the response variable. Now, when we square these residuals and then we add them up for each of the observations, That would be the residual sum of squares. The degrees of freedom in the denominator is the difference of the number of data points, which is 59 in this example, and the number of parameters estimated, that is 2. Why are there 2 parameters estimated? Because the slope and the intercept terms are being estimated. And notice that there is 59 data points because we removed 3 observations from the original data. Now, if you'd like to calculate this residual standard error manually instead of letting R do it, we can have a look at the following codes here. So we have a cbind function which binds 2 columns together. The first column is a vector of 1s that corresponds to the intercept term, and the second column is the predictor variable. And then we can multiply it with the regression coefficients, which you can extract by lm1.fit $coef, COEF. Now, once you multiply that, you get the predicted values of the response variable. And so the residual sum of squares is nothing but the sum of the squares of the residuals, which is the actual observation of the response minus the predicted values. The degrees of freedom is, of course, 59 minus 2. And we can take the square root of this ratio to get pretty much the exact same value as R calculated for us. Next, we are going to talk about the multiple R squared and the adjusted R squared. Multiple R squared is a measure of the proportion of the variability in the response that can be explained by the linear fit. What does this line mean? Well, check that at the end of the day, what we are trying to understand is how does the body weight vary? And is there a pattern in which the body weight varies if I know the brain weight? And I am trying to understand how the body weight varies as I'm varying the brain weight with the help of this regression line. So the better I can explain how the value of the response variable varies, given the predictor values, the better my model is. So this multiple R squared is a measure of how much of the variability I can explain by only using the predictor and using the linear fit. These R square values range between 0 and 1. A number near 0 represents that the regression did not really manage to explain the variability in the response variable. But a number close to 1 means that we did a good job. The model actually explains most of the variability in the response using the pattern captured in the linear fit. The problem is, for multiple R square, as you keep adding more and more predictors, the multiple R square value gets closer and closer to 1, as if we are doing a better and better job at explaining the variability in the response. The caveat is that even if you add a predictor that has got nothing to do with the response, the multiple R square tends to increase, which is a problem because we don't really want multiple R square to increase and make us feel like we are doing a better job when the predictors have got nothing to do with the response. So we look at the adjusted R square that corrects for the number of predictors in the model. So the adjusted R square is the preferred measure of how good the linear fit actually is. Finally, we have another p-value and another statistic that lets us make a global decision whether any of the predictors significantly affect the response. Well, this notion gets more clear when we tackle the next section where we actually have multiple predictors. In this case, we only have one predictor, and since the p-value is very small, we can say that there is a very high evidence that the predictor has an effect on the response. Next, we can look at some exercises if we have time at the end of the presentation, but if not, I would like you guys to repeat this above process on the full dataset and check the effect on the adjusted R square. And repeat the process after removing only 2 of these points that I have shown by this switch function. where the body weight is greater than 1000 and the brain weight is less than 5000, and try to figure out the observations and what it means for the adjusted R square. Next, we are going to focus a bit more on the prediction. So for the prediction, we have talked about the fact that the predicted value is the guess of the intercept term plus the guess of the slope term times the predictor value. We can also use the predict function, but for now, a little quiz for you guys. Try to predict using a simple linear model. For a mammal who has a brain weight of 87, can we use the formula 36.57 plus 1.22 times 87 to predict the body weight? Let us go back to the actual estimates and see if the model formula is correct and see if it works or not. So let us set up a poll and see if this answer is true or false. So for reference, let me show you the estimates. So to explain this question further, suppose you have a new mammal whose brain weight is 87. Can we use the formula 36.57 plus 1.2287 to predict the body weight? And remember that the formula here is beta naught hat plus beta 1 hat x. All right, so let me end the poll now. Thank you for your participation. We can see that the right answer is true because 36.5723 is indeed the estimate of the intercept term, and 1.2287 is indeed the estimate of the slope term. So the predicted body weight would be the guess of the intercept term, that is 36.5723 plus 1.2287 times 87. All right, so we can move on and so even though we can manually use the regression line formula to predict the response, a far better way is to use a predict function. So suppose you have a new data frame with brain weight information on it. So the data frame looks somewhat like this, that it's a data frame and it has only one column of the predictors. Here I have simply cooked up some examples, some numbers here, and I've pretended that these brain weights are correspond to 6 new mammals, and I would like to predict their body weight. So I can use the predict function here to perform the prediction. Now, what does this predict function actually require? It requires two basic inputs. The first input is I have to tell the machine that I am using the linear model stored in the variable lm1.fit for the prediction. Secondly, I have to provide to the machine the new predictor values for which I want to do the prediction. The point to remember here is that when you enter the new data, it has to be in the form of a data frame, not in the form of an usual vector. It has to be a data frame with a proper same variable name for the column. And if you use the predict function, you can check that the predicted values are given here without having to manually perform the calculations. Next, I would like to talk about the training error versus the testing error. Remember that the goal of fitting a statistical model is to denoise the data and extract the overall pattern. Remember that as we talked about the CARS data set right at the beginning, that there are often individual idiosyncrasies that correspond to different response values, even for same predictors or for different observations that we do not want to capture. We want to capture the overall pattern. So we need a good model learns how to separate the overall pattern from the individual noises, from the individual idiosyncrasies. So here are three plots and three fits. So we have the same scatter plot in the left plot, in the middle plot, and in the right plot. In the left plot is an example of underfitting, where the straight line, the blue straight line, does not really capture the actual pattern among the two variables x and y. The second one does a very nice job of capturing the overall linear pattern in the data. But what about the one on the right? This plot has a fit that tries to do too much. It's, first of all, not a straight line. It's a very complicated model that tries to fit every data point perfectly. But where is it going wrong? This particular plot is treating the individual idiosyncrasies as a part of the overall pattern. And that is where it's going wrong. So even though it seems like this particular plot fits every single data point perfectly, this is going to suffer when you are trying to do prediction on new values, because there it cannot fit to the individual idiosyncrasy of the new data point, right? And then the overall performance suffers. So when we are trying to evaluate performance on observations, we should always evaluate the performance on observations that are not used to train the model. That is why a standard approach while training a model, while learning a model, is to split the original dataset into two parts, a training part and a testing part. And then we pretend that we do not have the testing observations. We only train the model on the training part, and then we would like to check the model performance, like the prediction performance on the remaining observations, the testing part, and see how the model performs. So if you would perform something like that using a training and testing error, the model in the middle is going to perform the best. This brings us to the end of the section on simple linear regression. So I'm going to pause for some questions if you have on this section before we take a 5-minute break, and then we move on to the section on multiple linear regressions. Well, if you do not have any questions so far, then we are going to proceed to take the 5-minute break. We are going to start the next section at 1:48 p.m. in 5 minutes. So see you in 5 minutes. All right, let's get back to the session. Um, we are going to start about the scenario where there are more than one predictors. Multiple linear regression is that status where there are more than one predictors, but there is only one response. So in general, suppose that we have p distinct predictors, and in that case, the multiple linear regression model takes the form of y equal to beta naught, that is still the intercept term, plus beta 1 times x1 plus beta 2 times x2 plus all the way up to beta p times xp plus random errors. So the jth beta, so beta j corresponds to the association between the jth predictor and the response variable. Similar to the simple linear regression approach, we can estimate these regression coefficients and try to understand a pattern in the dependence between the predictors and the response. So let us take a look at an example and see how we can access the model performance, similar to how we have looked into the case of simple linear regression using adjusted R-squared. In this data set, there are 25 observations on age, weight, and blood fat content. We are going to fit a multiple linear regression to check whether age or weight or both affects the blood fat content. So you can run this particular cell to load the data set and have a look at the first few rows of the data set using the head function. So we have the weight, age, and blood fat, and we have the indices. Let us split the data into two parts because we realized that splitting the data into two parts and evaluating the model on the testing portion is what we should be doing. Because if we are only evaluating on the training data, then an overly complicated model that even treats all the noise as pattern is going to do perfectly, which is not what we want. So in order to extract some of the rows at random from the data set, we are going to use the sample function. The sample function by itself is a function that takes a sample of size that you can mention from a population that is described in the first input. So the first input is a vector of 1 colon number of rows in the data frame. So the population here is the set 1, 2, 3, 4, all the way up to 25. And these correspond to the row numbers. And we are taking a random sample of size 18. That means we are choosing 18 observations at random from these 25 observations that are available. So I create a new data frame called the df_train, which corresponds to the training data using this particular rows. And the remaining observations, notice the minus sign here, are from the test data. If I want to use a linear model and fit a multiple linear model, I use the same function, LM, and the overall structure of this function remains the same as before, that we use LM. We have the response, tilde, the predictors. But the only thing is that there are more than one predictors here, and so we separate multiple predictors by the plus sign. The data, of course, is the training data, not the entire data set. So we are going to pretend that we only have the training data portion to train our model. And then we can look at the summary of this fit to check how the model performed and what are the coefficient estimates. So the output looks very similar to the simple linear regression output, and most of the output interpretations are the same. The difference is that instead of having only two rows, we have a third row corresponding to the new variable, the new predictor. So we have a row corresponding to the intercept term, one row corresponding to the first predictor, and one row corresponding to the second predictor. The estimates are given here. It's 48, 1, and 4.9. The standard errors are given in the second column, and we have how many standard deviations is the estimate away from 0, and we have the corresponding p-values. Remember that like the simple linear regression scenario, the number of asterisks show how significant the p-values are. If the p-value is smaller than a threshold, then we say that the p-value is significant. Usually 0.05 is taken to be a threshold, so that if the p-value is less than 0.05, we say that the p-value is significant, and we do have evidence of a linear association between the variable and the response variable. The residual standard error, the multiple R-squared and the adjusted R-squared have the same interpretation as the linear regression, as the simple linear regression case. So for this example, 52.8% of the variability in the blood fat was explained by this regression model. A p-value of 0.00139, which is less than 0.05, shows that there is indeed at least one predictor among the predictors that have some linear relationship with the response. So now let us try to see if you can use these p-values and the concept that a smaller p-value indicates that the variable is significant in predicting the response, to see if we can identify the significant predictors between weight and age. So between weight and age as predictors for blood fat, based on the p-values, we have evidence of linear association between the response and which of the predictors. So let us have another poll and see which of the predictors have a significant effect on the response. All right, thank you for your participation. I'm going to end the poll now. And these are the results. I'm going to stop sharing the results and let us look at this question. So notice that corresponding to weight, the p-value is 0.4538, which is greater than 0.05. And there is no significance mentioned here as well. So for weight, we do not have sufficient evidence to claim that there is a significant linear relationship or linear association between weight and the response blood fat. But for age, the p-value is less than 0.05, and we have the 3 asterisks that shows the significance code that shows that this p-value is indeed significant. So only age is a predictor that has a significant association with the response. Very good. Next, we talk about interpreting the output. So we talked about the adjusted R-square and that around 57.74% of the variability in blood fat has been explained by the linear model. The p-value corresponding to the F statistic indicates that at least one of the 2 predictors has a significant effect on the response. So this is more like a global test, whether any of the predictors has an effect on the response or not. Next, let us move on to predicting the response given new data. Notice that we had saved 7 observations in our df_test as the testing data, and we would like to check how well the model performed on these new observations, these new predictors. So we are going to use lm1.fit to be the model which we're going to use to predict. And I'm going to use new data equal to df underscore test. Notice that this df underscore test is already in the form of a data frame because df1 itself was a data frame. So df underscore test is already in the form of a data frame. So the predicted values are in y hat. So we can compare the actual values, that means the blood fat for the test data, and the predicted values, and I put them by combining them into two rows using the cbind function. Now, if you want a numerical estimate of how well your method performed, you can look at the residual sum of squares that we looked at earlier. So 354 is the actual value of the response, whereas 362.41 is the case of predicted value. So the error we made is 354 minus 362.4119 to get the residual. So I can take the residual, square it for each observation, and then add them up. And then the residual sum of squares is a good notion of how well the model performed. As the quick exercise, I would ask you guys to repeat the above process with a 50-50 split between training and testing. So instead of using 18 observations for your training data, use say 13 observations and save the remaining 12 observations for the testing data and check how that affects the adjusted R-square and the residual sum of squares. That brings me to the end of multiple linear regression. So before I move on to the next section, which is logistic regression, I would like to pause for some questions. And if you have any questions in the chapter on simple linear regression or multiple linear regression, or if you'd like me to explain a certain concept in more details, you're welcome to ask that. All right, so if you don't have any questions, I'm going to move on to the next section where we start talking about logistic regression. Now, what was common in both simple linear regression as well as multiple linear regression? And what was common is that the response variable in both these cases is continuous variable. What happens when the response variable is no longer a continuous variable? What if it's a variable that takes only two values, 0 and 1? What happens when the response variable is not even numeric? Maybe it's labeled for two different classes. For example, you have observations on patients, and then your response is whether the patient has a benign tumor or a malignant tumor. So in these cases, you cannot really perform a multiple linear regression or a simple linear regression. Because suppose the response variable only takes values 0 and 1, and it only makes sense when they have values 0 and 1. How do you even interpret a predicted value of 0.34? In the case of logistic regression, we often tackle situations when the response variable are labels for two different classes. As I talked about the case of patients whose response variable is either their tumor is benign tumor or a malignant tumor. So you can code the benign tumors as 0 and the malignant tumors as 1. That makes the analysis very convenient. But at the end of the day, you have to remember that 0 has an interpretation. It corresponds to benign tumor. Malignant, 1 corresponds to malignant tumor. So a predicted value of 1.3 does not really make sense. So we would require a regression algorithm that is useful to classify the data into one of these two classes. So logistic regression is often used as a linear classifier, and it's called a binary linear classifier because we are interested in the scenario where the response takes only two values, 0 or 1. This is also the situation when you have a lot of incoming emails and you would like the machine to classify the emails as spam email or not a spam email, so that the response variable is spam or not spam, which you can code it as 0 or 1. So you can predict whether a new incoming email is spam or not. So the basic idea behind a linear classifier is to separate the two target classes by a hyperplane. What it means is that if you look at this picture here, suppose the two classes are shown by the colors of the dots. So we have a cluster of variables here or data points here that correspond to the class blue. And then we have some red dots here that correspond to a different class. Notice the hyperplane that separates the blue dots from the red dots. So if such a separation is possible using a hyperplane, then this training set or this data set is called linearly separable. And this is what we are trying to do in general using a linear classifier. So consider the situation where the response falls into one of two categories or classes. Using a single usual linear regression model might lead to non-interpretable predicted values, right? That is because in a usual linear regression model, the assumption is that the response variable is continuous. So how can we model the relationship between the probability that the response variable is 1 given x, that means given the predictors, and the predictors? So what we are trying to do is, instead of trying to work with the original response that only takes value 0 and 1 as our response variable, we are going to try to understand the probability that the response variable belongs to a certain class, which we usually take to be the class 1. So the probability that the response is 0 would be 1 minus this probability. So for response, for convenience, we are going to use the generic 0-1 coding for the response. So remember that we are no longer using the actual responses, the zeros and ones, as our responses in our model. We are going to look at something different, something that can be looked at as a continuous variable. So we are looking at a function of the original response variable. So this is why logistic regression belongs to a generalized linear model. Generalized because we are not working with the raw response variable. We are working with the function of the response variable. So this function is called a link function that maps the output to a probability. And the function that is used here is called a logistic sigmoid function that looks like as shown on screen. So the P of x, that means probability that the response is 1 given x, is equal to an exponential of a linear combination of the P predictors. Notice that this form in the exponent is what we had in the right-hand side of a multiple linear regression. But we do not have the same form here. We have an exponent of that expression divided by 1 plus exponent of that expression. And this particular form is called a sigmoid function. The beauty here is that after a bit of manipulation of the equation, it turns out that log of p of x by 1 minus p of x, this expression is nothing but beta naught plus beta 1 x1 plus all the way up to beta pxp. So we started with a response variable that takes only two values, 0 and 1, and somehow we ended up with a function log of p of y equal to 1 given x by 1 minus p of y equal to 1 given x that is continuous and that can be pretended to be the response of a multiple linear regression. Look at the right-hand side, and that is the same thing as the right-hand side of a multiple linear regression. But it is a generalized linear model because we are not working with the actual response. This quantity, p of y equal to 1 given x, which I have put it as p of x as a shorthand, divided by 1 minus p of x is called the odds. And since we have a log in front of it, we call this expression log odds or logits. So before I move any further, can you think of a reason if logistic regression can be seen as a case of supervised learning, or is it a case of unsupervised learning? So I'm opening a little poll here and see which of the options provided in the poll is actually true. I'm going to let you guys think about it and say 2 minutes to come up with an answer. All right. Thank you for the participation. And I'm going to end the poll now. And let me share the results. And let us try to go through these options. First of all, what is supervised learning? Supervised learning was, let's recall it, are situations where we provide the machine with the correct answers. So in these cases, when you have the observations, we also provide the response, which is 0 or 1. That means the correct class labels. So it's like telling the machine that this is the data and I'm telling you the correct class label. The sigmoid function that comes True, it is a part of the modeling that instead of working with the response, we are working with the function of the response. That's a part of the methodology, but it still remains, it's how the machine processes the information, processes the correct answers. It tries to take a function and then comes up with a model. But at the end of the day, the reason logistic regression is supervised learning is because it has those answers. So even though the relationship might not be linear because the responses are not actually zeros and one, and we are taking a non-linear function of the responses to connect it with the predictors. The concept of supervised versus unsupervised hinges on whether the correct answers are provided or not. So I'm going to stop sharing and thank you for your participation. Next, one more quiz for you guys. Let us talk about the idea of training error and testing error and try to see which of these three poles, which of these three pictures are going to do well for a testing error, not for training error. So we have, just to understand these figures, we have some dots, and the color of the dots correspond to the actual classes. The background of the dots show the predicted classes. For example, right where my cursor is in the left plot is a red dot which has been with a blue background. That means this red color has been misclassified or wrongly classified into a blue class. So among these three plots, which one of these is the best fit? So please try the poll and see which one of these plots provide the best fit. I'm going to wait for 1 more minute and then I'm going to end this poll. So try to think about trying to extract the overall pattern and not worry about the individual idiosyncrasies. All right, thank you for your participation. And these are the results. And let me explain why the middle plot is the correct one. So the overall pattern is that most of the data points on the top right diagonal are in the blue class, and that most of the data points on the bottom left diagonal is in the red class. Of course, there are a few individual cases where there are some red dots in the blue region and vice versa. But in order to capture this individual idiosyncrasy, the right plot deliberately tries to overfit the data and try to capture this noise by having a very complicated model rather than a simple linear classifier as is in the middle plot. Which is why on the right-hand side, even though it fits the training data very well, it's not the best idea to do this because it's going to suffer in predictive performance. Next, let us look at a database on breast cancer that was obtained from the University of Wisconsin hospitals. This data set is available online and you can check out the paper mentioned here. There are certain attributes for this data set that I would like to talk about, specifically that the response variable is class, where class 2 stands for a benign tumor, whereas class 4 stands for a malignant tumor. There are several attributes here, including the sample code number, clump thickness, and so on. Notice that all these numbers are numerical between 1 and 10. So you can use the code here to extract the data and have a look at the first few rows. However, if you look at the data types of each of these variables, you notice that the seventh variable is of type character. And you might wonder why, because the seventh variable, bare nuclei, is supposed to be numerical. So why is it stored as a character variable? Well, that's because there are missing information that have been coded as question marks in this particular data set. These things are something that you are going to frequently encounter when you are working with actual data sets. And so it is important to know how to extract these information, and I know how to remove this from your analysis or deal with it as you see fit as scientists. So the first aspect would be to remove this character data type and be able to correctly identify that these are actually numbers. So before that, we would like to replace these column names that are set default by R into something that is more intuitive and interpretable. So I have chosen the following column names as variable names from based on this attribute information. And I have BN specifically for bare nuclei. So once we have set the column names, so we have the data frame that looks like this. We have the BN column that looks like its characters. Next, we would like to recode the class variable so that instead of it being 2 for benign and 1 for malignant, I want to represent 0 being a benign tumor and 1 to represent a malignant tumor. So I can use the following code, once again using the which function to recode the class labels to 0 and 1. So I use those observations which have the class label to be 2. I have accessed that using the which df underscore L, because that is the variable name where I have the data frame. $class is equal to 2, and I have set the corresponding class values to be equal to 0. Notice the 2 equal to that corresponds to a conditional operator where we're checking that the class is equal to 2. And then I have the single equal to, that is the assignment operator, that I'm setting them to be 0. Similarly, for class equal to 4, I set them to be 1. All right. So now that we have tried to understand the which function, uh, which of the following codes would only extract the row numbers, only the row numbers of the breast cancer dataset DF underscore L, where the marginal adhesion coded by MA is greater than 5. So let us try to see if you understand the uses of the which function very well, and see which of the following little codes would extract only the row numbers, not the entire row, but only the row numbers. So here is a little poll for you guys. I'll give you 2 to 3 minutes to go over each of the codes and see which of them would correspond to extracting only the row numbers. A nice idea to solve this particular poll would be to go to your own Google Colab and actually run the options and see what you get. All right, I'm going to end the poll right now. Uh, and the results are this. All right. Um, the correct answer is the first option, which DFL $MA greater than 5. Because the question says, I want to extract only the row numbers, not the rows themselves. The second option gives you the entire rows. Because I have DF underscore L, the row number specified by the which DF underscore L $MA greater than 5 and all the columns. So the idea is to recognize that the which function is what gives you back the row numbers. What the second function does is that it gives you the data frame corresponding to those rows and whatever columns mentioned in the column area. So in this case, since nothing is mentioned, it is going to return all the columns. If you have more questions about this, please ask me these questions and I will answer them at the end of the session. All right. Notice that the column BN is of type character because there are missing values coded as question mark. So let us once again use the which function, but a little bit differently to see which of the positions in the data set have missing values which have been coded as question mark. So I use which df underscore L equal to question mark within quotes, comma, ARR.IND equal to true. What does this function do? Notice that df underscore L is not a vector, it is an array. It is the entire data frame, and we are checking for all the combinations of rows and columns where there is missing data throughout the data set. And the ARR.IND equal to true returns to us the indices of the array where we have the missing values coded as question mark. So notice that all the missing values are in column number 7, that is the BN column. And we have several different rows for which we have the missing observations. So the problem is the machine does not understand that question mark means that there is no information available. The machine gets confused that maybe question mark is some information, and that is something that the machine should try to understand and interpret. So we should tell the machine that these question marks are NA values. Setting them to NA helps us understand that these values are actually missing. So I am now going to not just extract the rows, but we are going to extract all these positions, and I'm going to set the value at these positions. That means df underscore L, and within square brackets, that means these positions will be set to NA. Once R encounters that the value stored in these positions is capital N, capital A, then the machine understands that, oh, there is no information here. The values are actually missing. So once I change them to NA and I check the type of the column, it still shows character. It still shows character because R doesn't yet know that the remaining values, that means the 10s, the 1s, and the 2s, that they had already interpreted it as character, are actually numbers. So we have to tell R that specifically, that df underscore L $BN is actually numeric. So I set it as a numeric vector, as s.numeric helps R understand that these values are actually numeric. Next, when I try type of the data now, it shows double, which is what we want, that these are actual numbers. So next, we're going to split the data into 599 training samples and 100 test samples. We build the logistic model on the training samples and test the performance on the remaining samples. So once again, we are going to use the sample function, which takes a sample out of the 699 rows, because if you check n row of the data set, it will be 699. And then I'm taking a sample of size 599. This function only gives you the row numbers that were selected at random. Then you take the corresponding rows and you take only those rows in your training data set. So df underscore L train row, comma, gives you the training data set, while the remaining becomes a testing data set. This is exactly as we had analyzed before in the previous sections. Now that we have finished splitting the data set, we are now ready to build the model. Since the response is binary, we are going to use a binomial family option on the GLM function. So we are no longer using the LM function. Why? Because we are now in the realm of generalized linear models. We are not using the original values of zeros and ones. We are using a different value. So that's why I use the GLM function. And we have to say family equal to binomial to indicate that the response variable only takes two values, 0 and 1. Now, once the binomial family is set, by default, R knows that we are setting a logistic regression. The NA.action equal to NA.exclude tells R what to do with the missing values. So the GLM excludes the observations with NA in them. So it handles the missing observations directly. Similar to before, we still look at the summary function to check out the output. So this is what the output looks like. And here are the coefficients. So quickly check that Bn, Nn, Ma, and Ct are the significant variables in the sense that they have the p-values corresponding to them to be less than 0.05. The remaining variables are not important because the corresponding p-values are greater than 0.05. So you cannot say that there is sufficient evidence to suggest a relationship between the variable and the response. One funny observation is that one of the variables indicated in this model was the indices, the IDs of the patients. Of course, you do not expect the IDs of the patients to have to do anything with the response. That means whether the tumor is malignant or benign, right? So as you can see, this model correctly captures that the p-value, very high p-value, indicates that there is no evidence of interaction between the actual response, the tissue being malignant or benign, versus the IDs of the patients. The predict function is once again going to be used to return the predicted values, but this time we have to be a little more careful. We cannot use the predict function like we have been using, because remember that in our model, if we set it up as a multiple linear regression form, the predict function is going to think that we are using the log odds as our response. So if you use the predict function without mentioning anything else, it's going to return the log odds as the predicted values, which is not something that we want. We want to work with the probability that the response is equal to 1. We want to work with the actual predicted values, whether we come to a decision that the tumor is malignant or not. We do not want to work directly with the log odds usually. So coming back to the predict function, so if I directly use predict and I use the variable that stores the logistic regression and I use new data equal to the testing data, the predict is going to return the log odds values. And notice that these values are continuous. Also notice that wherever there is NA in the observations, the predicted value is also going to be NA. So to avoid the fact that we are working with log odds and to work with the probabilities, we are going to use type equal to response. Type equal to response. Once you use type equal to response, you actually get the probabilities corresponding to the individuals, that the response is equal to 1. That means for patient number 6, there is a 99.9% chance that the person's tumor is malignant. Now, finally, we have to come to a decision that right now there is a 99.9% chance that this person's tumor is actually malignant. So do I come to a decision that this person's tumor is actually malignant or not? We have to come to a decision. Of course, when there's a 99.9% chance, it's easy to come to a decision. It's so close to 1 that we are going to say that, yes, of course, this patient probably has a malignant tumor. But if this probability is say 0.7, 0.6, how do you come to a decision? Well, we come to a decision using a threshold. We decide that if the probability that the person belongs to class 1 in general, or malignant tumor in this particular example, is greater than the threshold, then we are going to decide that this person belongs to that class, and that is going to be our predicted class. A very simple example of coming to a decision is when we look at the weather forecast for tomorrow and decide whether to bring an umbrella or not. So if the probability of raining tomorrow is greater than a threshold, we decide that maybe we need an umbrella. If the probability of raining tomorrow is lesser than a certain threshold, we decide that maybe we do not need to carry an umbrella tomorrow. So the action of checking the probabilities and coming to a decision is called prediction, right? We are making a prediction of whether it's going to rain tomorrow or not. So based on this thresholding, we can convert the actual probabilities to actual class labels. And for that, we are going to use the if-else function. The if-else function has a condition as the first input. The condition is being that this probabilities is greater than the threshold or not. In this case, the threshold is taken to be 0.5 because it's halfway between 0 and 1. So it's a very popular choice of a threshold. So if this condition is true, what do? We put it in class 1. If this condition is false, what do? We put it in class 0. So the if-else function has 3 inputs. The first input is the condition. The next input is what is the class label if the condition is true. The third input is what is the class label if the condition is false. And then we can run it and get the probabilities, get the predicted classes. Next, we're going to assess the accuracy of the model. So based on these predicted classes, we can check in the test data how many of the actual class label zeros did we predict to be of class 0? How many of class label 1 did we correctly predict to be class label 1? How many did we get wrong? How do we summarize this performance of the model? So we look at something called a confusion matrix or an error matrix that has a specific table layout that allows us to visualize the performance. Each row of this matrix represents the instances in the predicted class, while the columns represents the instances in the actual class, or vice versa. In the current example, first of all, let us remove the observations with NA values because the corresponding predictions are also set to NA in the GLM function. So we remove whichever observations is NA, and you can check which of the values in the vector y hat pred is NA by the is.NA option. Is.NA. And wherever this is.NA is true, I want to extract those rows, those positions by the which function. And then the minus sign says that I want to remove those positions. Right? So the y hat is a vector that has the predicted values, and the y true is the vector that contains the true values of the classes. Now, just to see if you guys remember what we should do regarding training versus testing error. So if you are trying to check for the testing error, is the statement true or false that the training data and the testing data should never have any overlap of observations, not even one overlap of observations? I'm going to give you guys, say 2 minutes to think about it and come to an answer. All right, I'm going to end the poll now. Thank you for participating. And the results are here. So let us try to understand why the correct answer is training data and testing data should never have any overlap of observations. That's because even if there is a few overlap, in that case, a model that overfit the data, that treated the noise as patterns, they're going to get an undue advantage for those observations. And we might end up choosing a model that is actually a bad model. So we should never have any overlap of observations between the training data and the testing data. Thank you. All right. Next, we are ready to construct the confusion matrix and evaluate the performance. We are going to look at two different ways to look at the confusion matrix. And first, we're going to use the package caret and use the confusion matrix function, which provides a lot of different information about the overall performance. But if we only want to look at the confusion matrix itself, visually, we can use the table function. So the library caret function is going to load the caret package. Now, if you run this, you might get an error that package caret not found. In that case, you have to use install.packages of caret to install the caret package, and then you can use the library function to load it. The confusion matrix, which treats the y hat and the y2 as factors. Factors because you do not want to treat them as continuous variables, but you want to treat the zeros and ones as two discrete values. So you have the factor of y hat and factor of y2. So if you run that, you get the following output. And this matrix here is basically the confusion matrix. So if you look at the rows, the row 0 corresponds to those observations that were predicted to be zeros. The row 1 corresponds to those observations for which the predicted value was considered to be 1. And the reference are the true values. So if you look at the intersection of the first row and the first column, the 0 and 0, for these 58 observations, the correct class was 0. That means the tumor was benign. And we correctly predicted that the tumor was benign. For the 36, that corresponds to predicted value 1 and the reference 1, that means these 36 cases had the tumor to be malignant, and we correctly predicted them to be malignant tumors. But for this case, this person had a benign tumor, but we predicted that this person had a malignant tumor. So we made an error here. But I would say that this is a very good performance, which is shown by the overall accuracy, which is a measure of the performance of the model. So 98.95% accuracy with a confidence interval of 94.27% to 99.97% is a very good performance. There are many other information here, many other measures of performance like sensitivity, specificity, detection rate, and so on, which is provided by the confusion matrix. But if you want to just look at the matrix, you can simply look at the table function. The table function just plots the values of y hat and y2 as a table, and you get back the confusion matrix. But the disadvantage is that it does not give you the other measures of performance, the accuracy, the sensitivity, which are all very standard measures of performance for machine learning models. And that is all that I have for this session. If you have any questions so far on any of the topics, or if you'd like to run into some error while you try to run these codes by yourself, or some of the poll answers does not make sense, I'm open to questions. We have 10 minutes. So questions, guys? Perfect. Well, if any one of you has any questions, feel free to ask me now. I would like to talk about some questions and that exercises that would give you more practice on getting used to using R to perform logistic regression and trying to interpret the model fitting and as well as the model outputs, the prediction performance using the confusion matrix. Here are a couple of questions and good luck then. Well, if you do not have any questions, let us try to bring this session to an end. I would just like to go through a couple of these exercises to give you a couple of ideas about how to solve them. For example, the B-Diag dataset also has a biopsy test for breast cancer, and the response variable is a diagnosis variable that classifies the observations into M for malignant and B for benign. So for this data set, you would have to recode the M and the B to 1 and 0 before you perform the logistic regression. You have to use texture mean and radius mean. There's two variables there, which you can see once you load the data set. The way that you load the particular data set is given here. So you can simply copy paste this line into a code. This is given in the form of a text here. And you can run it and see how the model performs. And there are two questions here that you can check. And since we have time, we can probably go through a couple of the exercises that was in the text. So for this exercise, repeat the above process with the full data set and check the effect on the adjusted R squared. So all you have to do is here, basically, instead of df1, you can just change the data to df. That is going to contain the entire data set. I just want to run this line and make sure that everything is fine. Scatter plot, I don't need to run it. And if I just work on the data equal to df, and if you run it, let's see what happens to the adjusted R squared. It's 87.05. So earlier, if we compare, we had adjusted R squared of 78.56%. So as you use more information, more data points, the adjusted R squared actually improves further. It will be interesting for you guys to check out what happens if you remove only these 2 points. Interestingly, you are going to observe that the adjusted R squares improves even further. And that is because these 2 points are actually very different from the linear model fit. And so they actually mess up the performance a little bit. So if you remove these 2 particularly, the remaining data points fit the regression line even better. So it would be interesting for you guys to check this out and observe that. And that actually gives you the idea of outliers in a data set, right? So I would like to bring this session to a close, and I would like to hand over to Christy to conclude the session. Thank you very much for attending.
Apologies for that. We'd like to thank Dr. Dasgupta again for today's session. Just as a reminder, our next session is going to be Thursday, December 16th, same time, 1 to 3 p.m. And This session will also be presented by Dr. Dasgupta on the topic of statistical learning classification. Thank you again.